In the second example of section 8.1, I want to demonstrate that not only we can treat a curve, such as this curve here, for example, as a graph of y equals to function of x, but also you can think of it as a graph of x equals a function of y. And so consider this problem, for example. We have to find length of y squared equals x from 0 to 1, 1. So this is the picture. We have, again, two branched curve, and we're looking at its piece, like so. So if we think of it as a graph of y equals square root of x, x between 0 and 1, then this is not a pleasant curve to study because, well, first of all, its derivative that we will need in order to set up our arc-length integral, its derivative is equal to 1 over 2 square root of x, which becomes infinite when x is 0. So we will have an improper integral to take care of, and furthermore, if you actually take the trouble of setting up this this integral, you will see that it is nothing but pleasant at all. So what we will do instead is we will think of this curve as a graph of x as a function of y. So we think of it as x equals y squared, and y, again, we can see from the second coordinates for these 2 points that y also changes between 0 and 1. Okay, so this is relatively manageable, so let's see what we have. So x prime, that is to say dx over dy, is simply 2y, and our integral can now be set up. So we integrate from 0 to 1, square root of 1 plus the derivative squared. So that is 1 plus 4y squared, and integration occurs in dy. Right, and so this here is now an integral that requires trig substitution. So we're going to do just that. We'll say that let's see, that 2y is equal to, so we have constant squared plus the variable squared, and so this corresponds to the case of tangent theta, and so it follows that dy is equal to secant squared theta d theta over 2, in fact. We put the 2 over here. All right, so let us rewrite our integral in terms of theta now. So we have integral that runs from, so for y equals 0, the lower bound is obviously 0 for theta as well. But the upper bound is a bit tricky. So you see, for the upper bound, let's say we have some theta 2 here. What do we know about theta 2? Well, we know that 2 times 1 equals tangent of theta 2, right? So this looks like an angle that has tangent equal to 2. This angle is not easily expressed through pi, and we don't necessarily care about it, not yet at least, right? Not until we actually try to evaluate this integral. So my suggestion is we just keep this angle as theta 2. So we'll call this angle theta 2, and for now leave it at that. And so in the meantime, over here I have 1 plus tangent squared theta, and then dy is secant is 1/2 secant squared theta d theta. Great, and then it appears I have to integrate from 0 to theta 2. secant 1/2 secant cubed theta d theta. Now, how do I integrate secant cubed? Well, we are supposed to know the integral of secant. We are not supposed to know by heart the integral of secant cubed. So how do I go from secant cubed to secant? You're correct. Either I remember the reduction formula or I don't, and then I just integrate by parts. So let's make this computation separately. So I want to integrate secant cubed theta d theta. And so I will do it using integration by parts. First, I set u to be secant theta. I set dv to be secant squared theta d theta. And so then v is tangent theta, and du is secant theta tangent theta d theta. All right. This gives me what? Gives me uv, so secant tangent minus integral of v du. So that's integral of secant theta tangent squared theta d theta. And so, well, that is secant theta times secant squared minus 1 d theta. And so I have secant tangent minus integral of secant cubed plus integral of secant. So it follows that integral of secant cubed theta d theta equals 1/2 of secant tangent plus integral of secant, which I already know. So that gives me 1/2 secant tangent plus, so for secant theta, I have the antiderivative log of secant theta plus tangent theta. Like so, and then plus a constant. Great. Now going back to my integral, I see that I have 1/4, and then I have to plug in my expression here, secant theta tangent theta plus oops. Just want to move this part here to be able to complete the problem on the previous page. Okay, this like so. So now in here I have what was it again? Secant theta plus log of the sum of these two. All right. Yeah, and then I have the difference from 0 to theta 2. Now the beauty of this question is that I get to actually evaluate this difference from 0 to theta 2 without knowing what theta 2 is. So I don't specifically care about what is theta 2, right? I only care about what is the value of secant of theta 2. That's it. And so this is what I get to use. I use that secant theta 2 is equal to 2, because that's how we define theta 2. Right, it corresponded to the upper bound here, so that's when y was 1, and so that's what I get. And that means that tangent theta 2 is square root of secant squared theta 2 minus 1, right? The tangent is positive because when I use the substitution y equals tangent theta, I'm looking at the right half plane. For when secant is positive. And so I'm integrating here in the positive direction from 0 to some angle. For that angle, secant is 2, and so it follows that tangent is also positive, so I need to put the plus sign here in front of this square root. Yeah, and so this gives me what value again? This gives me square root 3 for tangent. Wait a second. Oh, that's not, I'm sorry, that is not, okay, so that makes sense actually. That's not tangent theta 2, that is equal to 2, but not secant of theta 2 that is equal to 2, but tangent. Right, so then I actually do know tangent. And I want to determine secant, but still both secant and tangent are positive, so I only keep the plus in front of the square root. And that gives me square root of 5. Good. So what do I see now? Well, I know the value of tangent of theta 2. I know the value of secant of theta 2. Now, what are the values for what is the value of this expression for theta equals 0? Well, when theta is 0, the first term vanishes because I have tangent of 0. For the second term, on the other hand, I have log, or absolute value of secant of 0 is 1, tangent of 0 is 0. So I have 1 plus 0, and then I have log of 1. So the second term here also vanishes for theta equals 0. And hooray, I win. I have 0 for the entire lower bound, and I have 1/4, let's see, square root 5 times 2 plus log of 2 plus square root 5 for the upper bound. And this completes the evaluation of the arc length for this curve here.